Welcome back. In this video, we're going to learn about periodic trends. Specifically, we'll learn about the periodic trend of atomic radii and how it relates to the location of the elements on the periodic table. Then, we'll also discuss the relationship between atomic radius and reactivity when discussing a chemical family or a group of the periodic table. To understand the trend of atomic radius, we first need to define what we mean by atomic radius. You can see here two different depictions of two atoms. On the left, we see that the atoms, the edge of those atoms are just barely touching. Whereas on the right, you can see that the atoms have overlapped. And so the distance between the center of the nuclei is smaller in the case on the right and in the case on the left. The case on the left, we call this non-bonding. This would happen if the atoms come up and they collide, they bounce off of each other, kind of like billiard balls. On the right, this is called the bonding radius. And this is found when you have multiple atoms that are bound to each other. When we look at the atomic radii, which is plural for radius, atomic radii of different elements, of the main group elements, we can see that there are trends. So the values that are listed here on the screen are the bonding radii of those elements expressed in picometers. And what you can see is that there's a trend going vertically as well as horizontally. So when we go down a column, we go down a family, we see that the atomic radius always increases. Now, the amount that it increases by does not stay the same, but we do see that it increases as we go down a column. And it turns out that the reason for this is because as we go down a column, we're increasing the number of shells that are being occupied by electrons. Remember when we talked about electron configurations, we discussed that elements of the same group have increasing shells that are being occupied. Therefore, those electrons are being held farther and farther from the nucleus, which increases the size of that atom. Now, as we go from left to right, we see that the atomic radius is always decreasing for these main group elements. And the reason for that is because as we are adding additional protons into the nucleus, this pulls the electrons in closer. Remember, when we talked about the structure of an atom, the vast majority of the atom is empty space. So when you add in a proton, it's only occupying a very small amount of that space. So even though we're adding in protons, those are not increasing the size of the atom, but rather they're causing it to shrink because there is a larger attractive force pulling the electrons in towards the nucleus. All right, let's try a practice problem here. Let's see if you can determine this. You will need a periodic table to solve this, but pause the video and see if you can determine this on your own. Welcome back. So we want to order the following elements in order of increasing atomic radius, so from smaller radius to largest radius. So in order to do this, you need to evaluate the periodic table and the location of those elements with respect to each other. What we can see here is that there are some comparisons that can be made because we have multiple elements in the same row as well as in the same column. So we know that elements that are in the same row, going from left to right, have a trend. That is that they get smaller as we go from left to right because we're increasing the number of protons. We also know that elements in the same column, in the same family, are larger as you go down because we're increasing the number of shells. You can kind of think of it like adding layers on. As you add, if you're just wearing a t-shirt, then you add a sweater, then you've gotten larger. And as you add on a coat on top of that, then you've gotten larger yet again. So what we can see here is we would be able to rank these by their atomic radius, and the values are listed here as well. So when we line them up, we see that chlorine is the smallest, then magnesium, then barium, and then cesium. Okay, the last thing we want to look at here is how the difference in size for these elements within the same group affects their reactivity. As I've mentioned before, elements in the same group have the same valence shell electron configuration. What that means is that they have the same number of valence electrons, and therefore they behave similarly to each other. So they're going to have very similar reactivity. They'll behave in similar ways. However, elements that are larger, but within the same group, tend to be more reactive. The reason for that is because the electrons are held less tightly in the larger atoms, and therefore they are easier to remove. So we can see similar patterns of reactivity for the alkali metals. That's that first group where they have a noble gas core followed by one electron in the s block. The alkaline earth metals, which have a noble gas core, followed by 2 electrons in the s block. And then the halogens are also another main group that have similar characteristics. Yet as we go down, those electrons are easier and easier to remove. So that's it for this video. Thanks for watching. Have a great day.